So this is a question of EMI, also some amount of rotation, basic ones only, and it is from DC Pandey sir's book. So let's solve it. Yeah, basically, in simple terms, we have a fixed like ceiling here, and a metallic wire is drawn, and here it is fixed. It is wound around a ring of radius r and mass m, and here is also a wall which is smooth, and it's given in the question, and also it is infinitely long. So what can we conclude is that friction won't act, and secondly, this is also conducting. Then later, here a resistance R is placed. Now also there is field, magnetic field to be precise. And what will happen is, if it is like left from here, earlier it was held at this position, then later it's left. Now my first thought of this question was that the change in flux will be zero, because what flux was initially, after even after it goes down, the flux will be same. But that is kind of a wrong approach, I would say, because due to that approach I would never be able to solve. That approach will tell zero current will flow, and in the question it is asked that we have to find one current in resistance as function of time, and two terminal velocity. So let's draw, I mean it's drawn already. Now what do we know? We know that it will experience a torque initially due to gravity, and we know this will provide tension T up here, and it's sort of hard to calculate. That's why we are finding torque about this point. And as we know that the force due to this wall will be passing through this, so torque will be zero. Now let's write the equation, which is the equation of torque first. This is this, then let's find torque. Torque is equal to mgr, and also you can realize when this is like rolling down, this fixed, it will be sort of pure rolling on this. So we can say that the projection of this will act and the projection of this will act, that is, they will be like this, and sort of like you can it will help to visualize these two batteries. The EMF will be same, the reason as they have same velocity, and also their projections are same, and the length will be 2r, so E will be B into 2r times V, the velocity. Now we were writing torque. Talk about this would be mgr due to mg, and in the upward direction, due to the current flowing here let's say I by 2 will flow, here also I by 2 will flow, as here we are assuming I. The reason here we are assuming I is because current in R as function of time is asked, and assumed I here. Then the force on these two, as these are moving, will be BLV, sorry, BIL. I is I here, actually I would be E and R, so potential difference should be same due to Kirchhoff's law. So IR equals E, so I equals E by R, which is B 2BRV by R. That's the this is the resistance, that's the radius. So here should be IR. I made a mistake because the radius and the resistance are different. 2BRV capital R. Now coming back to the torque equation, the force will be equal to, wait a second, the force will be equal to minus BIL divided by okay, no, just torque. So torque is this into the radius. Here the radius should be this. If you write alpha equal to torque by inertia, this will be equal to something like, so I about this point will be, here is mr square, here is 2mr square, so 2mr square, and here mgr minus bilr, and this gets cancelled. Now alpha equals mg minus bil 2mr. Okay, so as you know, it's pure rolling. So let's look at the pure rolling here. This is the string and it's wound around this several times. Now it will sort of roll like this. It will roll this way and then like pure rolling, just as in case of the floor. So we can assume that if this is V, then this point should be at rest. For this to be at rest, this and this should be equal. This will be, as it's rotating this way, this will be omega r, and this will be V as center of masses, velocity is V. Now V equals omega r. This is derived earlier also, no need to derive it again. If you know, it's very good. So I'm here using the same result as pure rolling on string. V equals omega r and A equals alpha r. Now you can write alpha as, from here, A by r equals mg minus b. I is written here already, no need to worry about that, by mr. So this should be this r because it's the radius, and this and this will obviously be multiplied, so it will get cancelled. A is mg minus bil, and L here is, notice this projection. Basically this projection will receive the force, and therefore sort of like this, these will receive force in this direction, so its projection will also receive the same force, and this is 2r, so L is 2r. Basically we can replace L as projection. It's simple, so I'm not writing the reason behind it. That's it. And you can see here variable is I only, mg will be constant, and also A is variable. So what if we differentiate this? Will it work? Let's first substitute I there. We substitute I as 2b rv by capital R. B square r square 4v by r. That's it. Then we have here A and a V. So to solve this, we can clearly do this. dv by dt mg minus 4b square r square v by r. This will be a bit complicated, but if we solve this differential equation, we would get something like, let's take it in the denominator, this whole term there and dt there. So mg minus, let me write it here, 4b square r square v by r dv, and that's equal to dt. If we integrate both the sides from 0 to v later, let's say terminal velocity v, and from 0 till t. This is not terminal velocity, we are finding v as a function of t. Then for that we are going to do this. After this we will have ln of minus mg minus 4b square r square v divided by, because minus ln, then there mg is equal to t. And if this is like a differential equation, we first had to integrate this using the chain rule. This will be in the denominator, so I'm taking it there. So like 4b square r square v by rt, so ln minus mg minus 4b square r square v by r divided by mg. It's very lengthy term, I don't know if it's right or not, but we have to find the terminal velocity. Now terminal velocity is like a velocity which will be reached at t equal to infinity, right? So we have to solve this, and this you can get an idea. It's sort of like in conductors, in capacitors or in inductors, right? Because E will be there and all. So if you take this minus there and solve this, I guess you will be able to do that in your head itself. No need to like visualize it so much. Let me also think about it. So mg, firstly it goes e raised to power minus 4b square r square vt by r, like this. And then later on, wait, if I had done it in this book itself, it's fine, but never mind. Then take mg there. If you take mg there, you take this term there, mg multiplied by this mg minus, okay, so 1 minus e power this into multiplied by mg is equal to this whole term. So this is the solution of that. What is that? Let me see. That is basically 4b square r square v by r. So the simplifying, we'll get v equals mgr 4b square r square 1 minus e power minus something something and t. If we put t as infinity, because it's minus, this term will become 0 at t equals infinity. Now when it gets 0, our answer will be this. Let's check the answer. I don't know if it's correct or not, but we found out is terminal velocity. 14th answer is something like this, mgr by 4b square r square. Okay, let's go, it's correct. Now also the thing asked is the current and the resistance are as a function of time. So for I, obviously the thing in our mind is this itself. We can substitute this here. I equals to b r v by r. So we can substitute this v. It would be a very very like bad looking term. 2 gets cancelled, 1 by 2, r gets cancelled, br gets cancelled, so br is left, and m is left. 1 minus e power minus 4b square r square vt by r. Okay, sheesh, like this term. Let's check again. 14th, I guess so, hope so, it's right, but one thing is not matching is here I'm getting 4 and in the solution It is 2 raised to power 2. I don't know why this is wrong, but let's see. Somewhere I've done mistake. Either ways, thanks for watching. Hope you have a good day.